Carlos said, "I've spent my life trying to propagate a particular theory about the universe. Then this happens. The hypothesis is focused. I welcome this test, because it's through research that science advances and gains momentum." In essence, the James Webb Space Telescope challenges some long-held cosmological beliefs that have been taken for granted for a century. Another image from ultra-trackdown shows that we have made a mistake in our exploration of the universe. The telescope is somewhat problematic. It was designed to detect the main stars of the universe. Previous views may provide completely new and valid perspectives. While some scientists are disappointed by these new findings, others welcome the progress made, as it has long been clear that previous hypotheses were wrong. The anomalous phenomenon itself may raise concerns in determining the rate of evolution of the universe. In any case, scientists have stuck to old assumptions for a surprisingly long time rather than deciphering these warnings accurately. The oldest light in the universe, known as the cosmic microwave background, CMBR, was created about 380,000 years after the Big Bang. At that time, the universe had cooled enough for protons and electrons to combine into stable hydrogen particles. The resulting reionization made the universe transparent to light. American scientists Arnold Penzias and Robert Wilson first discovered the cosmic microwave background in 1964 while developing a new radio receiver technology. They heard a continuous sound coming from above them, all around them. The Big Bang theory was initially thought to be fully supported by this discovery. Wilson and Penzias shared the Nobel Prize, and their discovery became an important precursor to later developments in cosmology. The microwave background radiation, CMB, illuminates the early universe, and subtle changes in temperature provide important information about conditions immediately after the Big Bang. Scientists use the CMB as a reliable indicator to estimate important aspects of the material universe, such as the rate of expansion of the universe. Edwin Hubble had previously made such estimates in the late 1920s. He discovered that galaxies far from us are moving in all directions and that there is a dependence of velocity on distance between them. This relationship is now known as Hubble's law or Hubble constant. Hubble's calculations were not as accurate as they are now, but they were instrumental in the discovery of the cosmic microwave background radiation. After recalculating the expansion rate, experts found that it was much lower than Hubble's original prediction. The discrepancy in the expansion rate estimates has been known since the 1990s. However, by recalculating the data using type Ia supernovae as standard candles, a more accurate estimate was obtained. Experts have pointed out that there may be a problem with the universal expansion theory or the way the CMB data is processed. This discrepancy, also known as the Hubble voltage or S8 voltage, raises the possibility that there is a serious problem with our current understanding of the universe. The James Webb Space Telescope, JWST, has provided amazing data that could help clarify the issue from the beginning. Ancient and advanced worlds that may have formed before the Big Bang are challenging long-held scientific beliefs. The idea of how fast the universe is expanding and how it all happened is under serious investigation and is considered one of the greatest challenges facing astronomy today. Recent images show a very different universe than previous models. The S8 tension heralded the realization that our knowledge of the universe may be flawed, and this has left researchers struggling to stick to outdated theories. Many researchers are confused and frustrated by this uncertainty. To address this situation, we need to understand how science works. To arrive at a conclusion, hypothetical scientists combine observed data, mathematical models, and logical reasoning. They learn through speculative analysis, test results, and strange observations. The word theory itself implies concepts and inventions, not absolute truths. Our rational understanding comes from data from neutrino and gravitational wave detectors, images from telescopes, and sound and radiation from radio telescopes. Now, thanks to the James Webb Space Telescope, we can study ancient light in unprecedented detail, breaking it down into different frequencies. We can map the elements, masses, and number of stars that existed in the galaxy billions of years ago. However, Webb's image may have certain flaws. For example, gravitational lensing can make it difficult to distinguish between galaxies and black holes that emit light of similar intensity. Our knowledge has grown to accept various scenarios as part of a whole, often ignoring competing theories. Recent discoveries from the James Webb Telescope provide important clues that allow us to replace old hypotheses with more insightful ones. These results are so surprising that scientists are currently struggling to come up with new interpretations. Many experts are concerned about recent discoveries that shake the foundations of physics. Today's physics is still deeply influenced by the discoveries of Isaac Newton in the 17th century. His equations of motion and gravitation have been the cornerstone of our knowledge of the physical universe for thousands of years. While Newton's laws work perfectly on Earth under normal conditions, they needed to be extended in space, a task pioneered by Albert Einstein in the 20th century. Einstein's special theory of relativity, published in 1905, changed our perception of reality by showing that the laws of physics depend on the speed of the observer. After publishing his general theory of relativity in 1915, he extended these concepts by using mathematics to predict gravitational anomalies caused by the curvature of spacetime by massive objects such as galaxies and stars. Many aspects of Einstein's theory were obvious, but he recognized its limitations and tried to develop a consistent structure, but failed. This is an undertaking that no scientist has yet succeeded in. It is fun to try to figure out where the mistake is. The famous American astrophysicist Michio Kaku has suggested that solving this puzzle would win him a Nobel Prize. We need to investigate whether we have misinterpreted reality, misinterpreted anomalies, or whether there is a problem with the telescope itself in a cosmic crisis. Dark energy and dark matter are prime suspects, but neither dark matter nor dark energy has been explicitly detected or proven to exist. Current models show that together they make up about 95% of the universe. They may not even exist, or they may have properties that we do not yet know about. The idea that dark matter's properties have changed over time and may now be displaying intelligence is currently being discussed. The expected behavior of gravity, which generates attraction through mass or spacetime curvature, has not been conclusively shown. Despite the multiple confirmations of Einstein's theory of spacetime curvature, it is still possible that gravity has unexpected properties or that gravitational attraction is caused by other phenomena. In cosmology and space exploration, certain features have been recognized as fundamental constants over time, and their invariance has helped to establish their reliability. Small differences in these constants are calculated to provide new information about the universe and to explain events that do not require dark energy. Our misinterpretation of the motion of light may have led to inaccurate measurements of galaxy distances and ages. It is possible that we have misinterpreted the cosmic microwave background radiation, or that our assumptions about the nature of space are incorrect. The Big Bang theory is likely to be challenged by the possibility that the universe did not have a single origin. It is impossible to completely rule out small flaws in the Webb telescope or other observational instruments. Scientists and experts agree that errors in data management, equipment, or interpretation are always possible. Cosmological ideas are constantly being reevaluated, highlighting a fundamental aspect of scientific progress: the ability to change and improve our understanding in response to new evidence. The discovery of the James Webb Space Telescope marks a major turning point in our quest to understand the mysteries of the universe. Beyond simple technological leaps, it is important to understand the broader context and implications of such rational shifts in cosmology. When we encounter these ideas, the process is often motivated by the need to adjust theories in light of new information. While the discovery of strange anomalies or contradictions in accepted ideas can be unsettling, it also represents an important opportunity for scientific progress. In cosmology, theoretical models are built to provide an accurate basis for understanding the origin, growth, and evolution of the universe. But these models must be tested and, if necessary, updated as new information becomes available. The nature of dark matter and dark energy, which are central to modern cosmology, is one of the major research topics. It has been suggested that the difference between the mass expected from visible matter alone and the observed rotation of galaxies could be explained by dark matter, an invisible type of matter that does not emit or absorb light. In the same vein, the apparent rapid expansion of the universe has been explained by the introduction of dark energy. However, dark matter and dark energy remain a mystery and play a major role in current models. Ground-based studies have so far been unable to detect them clearly. This has led scientists to explore many theories and plausible explanations. Another obstacle to understanding dark matter and dark energy is the sheer scope of cosmological research. Indirect evidence for these components comes from observations of distant galaxies, the cosmic microwave background radiation, and other large-scale events. But their exact composition is still unknown. Scientists are considering a range of possibilities as a result of this ambiguity, from changes in current models to entirely new principles. Some theories suggest that dark energy could be a new fundamental force, or that dark matter could be made up of more exotic particles than previously thought. Another fascinating area is the study of cosmic inflation. The rapid expansion of the universe in the early stages of the Big Bang is explained by this hypothesis. This idea has gained popularity recently as researchers study the role of quantum fluctuations in the early evolution of the universe. The powerful application of the theory of cosmic inflation could help clarify issues related to the rate of expansion of the universe. It helps explain why the universe appears flat and why the cosmic microwave background radiation has the properties we see today. Observations by the James Webb Space Telescope will undoubtedly play a significant role in expanding our understanding of cosmic expansion and its impact on cosmic evolution. Researchers are also developing the concept of a multiverse, which suggests that our universe is just one of many parallel universes. This idea could change our understanding of cosmology, because it implies that physical laws could be different across universes, resulting in different forms of matter, energy, and expansion rates. The goal of the scientific community is to combine these diverse theories and ideas into a single framework that accurately describes how the universe works. Recent discoveries from the James Webb Space Telescope could provide important insights into the nature of dark matter and dark energy, helping scientists improve or modify the standard model of cosmology. Ongoing research and discoveries using instruments like the James Webb Space Telescope are challenging us to rethink our understanding of the universe. We face uncertainty and mystery regarding the nature of dark matter,